In the last section of chapter 13, I'm going to talk about reaction mechanisms and catalysis. Now, I'll warn you right now, this is probably going to be a somewhat long video, but I'll try to keep it as short and concise as I can. So up until now, we've been talking about reactions as overall reactions. We see a reaction on paper, we consider that to be what happens when two reactants are put into a container and left to react. But most reactions actually occur in a series of steps, and the balanced chemical reaction or chemical equation that we see on paper doesn't tell us how the reaction actually occurs. So there are often a series of steps which add together to give the overall reaction, and the series of steps is called the reaction mechanism. And we'll talk about those steps in this section. So a reaction mechanism is a proposed set of steps that describe how a reaction occurs, and each step in a reaction mechanism is called an elementary reaction. An intermediate is a species produced in one step of a reaction mechanism and consumed in a later step, and the molecularity of a reaction just refers to the number of reactant ions, atoms, or molecules involved within one of those elementary steps. So remember, an elementary step represents a single process, like a single collision. So let's consider this following reaction. We have two NO2Cls. That produces two NO2 gas plus a chlorine gas molecule. So the following two reactions are proposed as elementary steps in the mechanism of an overall reaction. So we have step 1, where the NO2Cl breaks down into NO2 and Cl gas, and then step 2, where another one of those NO2Cls reacts with the chlorine that was produced in step 1 to produce the NO2 and the Cl2. So a couple questions we could ask are, what is the intermediate in this reaction mechanism? Remember, an intermediate is an atom or a molecule that is formed in one step and then used up in another. So in this case, chlorine is formed in the first step but then used up in the second step, right? So it's a product in the first step but a reactant in the second step. And another question, what is the molecularity of reactions 1 and 2? That's simply counting the molecules that are involved in each of the steps. So in step 1, we have one NO2Cl gas molecule. So the molecularity of step 1 is unimolecular. And in step 2, we have one NO2Cl molecule, one Cl gas atom. And since there are two molecules in the reactant side, we call step 2 a bimolecular reaction, right? So it has a molecularity of 2. Now, since steps 1 and 2 are part of a reaction mechanism, then we call these elementary reactions. Now, here's another example. We have a two-step reaction. There's step 1, NO plus NO producing N2O2. Step 2, N2O2 plus O2 producing 2NO2. And if we look at what the overall reaction is, we have two NO gases plus an oxygen producing two NO2 gases. Now we should be able to look at the reaction mechanism and be able to derive the overall chemical equation. So if we look at the overall reaction, we have two NOs, and in our reaction mechanism we have two NOs in step 1. In the overall reaction we have one O2, and in step 2 we have one O2. In the products of the overall reaction we have two NO2 gas molecules, and in step 2 of the mechanism we have two NO2 molecules. And we have both an N2O2 on the reactant side of step 2 and the product side of step 1. So since this is a molecule that was first produced and then used up, it's an intermediate, and intermediates are not included in the overall reaction. They essentially cancel themselves out, right? Because it's produced, then it's used up, so it's no longer there as part of the overall reaction. So now let's see how reaction mechanisms relate to the rate law. So we've talked about rate law in the previous couple of sections, and we hopefully understand that this little 2 here means that it's second order. This is a concentration of a reactant, and the rate is here, and the rate constant is K. Now, if we have this particular reaction, two NO2s producing two NOs and an O2, and it's observed that the rate law equals K times the concentration of NO2 squared, we're saying that the reaction is second order with respect to NO2. But this is an overall reaction up top, and if we were to propose a mechanism by which this reaction occurs, we could break that up into 2 steps. So we have step 1 and step 2 below. Now, one thing about the rate law is that it must relate to one of the elementary steps. So it doesn't relate to the overall reaction, and it doesn't relate to all of the elementary steps or all of the steps in a mechanism. So the rate law depends on what's called the rate determining step, which is the slowest step in a mechanism. So there's always going to be a slow step. You could compare this to your commute to school. So for me, the rate determining step is my drive because it takes me about an hour. I can get up and get ready in less time than it takes for me to drive to Eastern Michigan University. So that's my rate determining step. So that's my slowest step. So the time that it takes me to get to work is going to depend on traffic, for example, how slow that driving is for me. So the rate law depends on the slowest step in the mechanism, and it's also related to it. So if we know that the rate law is second order in NO2, we can look at the mechanism and notice that step 1 has an NO2 in it, and it also has a 2. That 2 is this 2 up in the rate law. Now, we learned before that rate laws can only be determined experimentally. Remember, I think this was in the second video when we're talking about how to determine rate laws from a table of data. The exception to this rule is that rate laws can be determined directly from the rate determining step, or the slowest step in a reaction. So you can directly look at the stoichiometry of an elementary step. If it's the slowest step, you can derive the rate law directly from it. Okay, again, this is not the case with overall reactions. It's only the case with elementary reactions. And the other thing that has to be true is that the sum of the steps of a reaction mechanism must equal the balanced chemical reaction, just like we've seen in the previous 2 slides. So here's a view of a reaction energy profile or a potential energy diagram like we saw in the last section. But notice that there is more than one bump in this. So each of those bumps represents one of the steps in the reaction mechanism. So there are actually 2 activation energies, one for each step. So the activation energy for step 1, you can see right here. The activation energy for step 2, you can see right here. And remember what we said about activation energies as they're related to the speed of a reaction in the last video. The higher the activation energy, the slower the reaction, right? So in this case, step 1 is going to be the slow step because it has the highest activation energy. Once the reaction reaches that first bump, it's reached the activated complex, or the first transition state in this case, and then it will fall down the hill, go up another little bump, right? The activation energy is not as great in this case, but it will still go through another transition state, another activated complex, before it finally reaches the products at the end. All right, so let's go through an example. So a proposed reaction mechanism for the reaction of nitrogen dioxide and fluorine is as follows. So we're considering these as 2 elementary steps in a reaction mechanism. The rate law was experimentally determined to be K times the concentration of NO2 times the concentration of F2. So we're saying that this is first order with respect to nitrogen dioxide and first order with respect to fluorine. So given this information, which reaction is the rate determining step? So remember, the rate law must relate to the rate determining step. So if we have an NO2 and an F2 in the rate law, we're going to be looking for those same components in the reactants of one of the elementary steps. So we can look at step 1, we have 1 NO2 and 1 F2. So this reaction 1 must be the slow step or the rate determining step. So part B asks, how do you know that this is the rate determining step? And again, we know it because the rate law matches the rate determining step. And if we were to write the overall balanced equation, we notice that we have a fluorine that is on both sides of the equation, so it's an intermediate. We have 2 NO2s, 1 fluorine gas, and on the other side of the equation we have 2 NO2F gas molecules. So the overall reaction is going to be 2 NO2 plus F2 produces 2 NO2F. And I should put the phases there. Everything is a gas. Okay, another example. Nitrogen dioxide reacts with carbon monoxide to form nitrogen monoxide and carbon dioxide. Here's the following reaction mechanism that's been proposed. We're being told which reaction is the slow reaction and which one is the fast reaction. So given that information, how do we write the rate law? So again, the rate law is related to the rate determining step or the slow step. So all we have to do is look at this, look at the reactants, and write out the rate law. So rate equals K times the concentration of NO2 squared, because there are 2 NO2s. Okay, so there's our rate law. Write the overall balanced equation. Again, what do we have? We have an NO3 as an intermediate, and we also have 1 NO2 that will cancel out. So the overall reaction is going to be NO2 plus CO produces NO plus CO2. Write the intermediates in the proposed mechanism. Well, we have only one in this case, actually. We have NO3 as an intermediate. Remember, an intermediate is something that is produced and then used up. And then what step is the rate determining step? Well, we know it's a slow step, so it must be step 1. Okay, so now we're going to be looking at how to know if a proposed mechanism is actually something that's valid or can be possible. So the criteria for a valid mechanism are that the sum of the elementary steps must be consistent with the stoichiometry of the overall reaction. In other words, you must be able to add up those elementary steps and it should equal the overall reaction. The rate law has to be based on the molecularity of the rate determining step. So again, the rate determining step and the rate law must match in terms of both the components present, the molecules that are there, as well as the exponents must match the stoichiometry, right? And as I've stated before, if the elementary reactions are known, the reaction order, which is again the exponents in the rate law, can be written directly from the stoichiometric coefficients of the rate determining step. So let's look at this particular reaction here. We have 2 NO2 producing 2 NOs and 1 O2. We have the observed rate law. Rate equals K times the concentration of NO2 squared. And we have a mechanism where we're told that step 1 is slow, step 2 is fast, and we're also given the overall reaction. So is this a valid mechanism? So let's first check to see if the overall reaction matches what we expect. Okay, so we'll look at the reaction mechanism and we'll see that an NO3 cancels and we're left with 2 NO2s, which is the same as the reactant side here, 2 NOs, which is shown here, and 1 oxygen, which is there. Now we look at our overall reaction from our proposed mechanism and look back up at the top of the slide to see if it matches the overall reaction, and you can see that it does. So criteria 1 has been satisfied. Now we look at the rate law. So the rate equals K times the concentration of NO2 squared. So the rate law is second order with respect to NO2. And this is going to come from the slow step of the reaction. Slow step is step 1. If we were to derive the rate law directly from the first reaction, we would get exactly the same rate law that is observed. Rate equals K times the concentration of NO2 squared. Because again, there's our NO2, and this 2 in the stoichiometry is the same as the 2 that is in the rate law. So it seems like this is a valid mechanism because the 2 criteria that we've discussed in the last slide fit. So how is it that we can actually find reaction mechanisms? Well, it's something that we have to actually do experimentally, and we have to basically look for different components of a reaction. So be able to measure intermediates, be able to measure different components of the different steps. So it's not something that's really easy to do. So again, when a reaction mechanism is proposed, it has to satisfy the 2 criteria that are on this slide. So let's go through another kind of example here. So considering the decomposition of hydrogen peroxide, so hydrogen peroxide going into water and oxygen. If experiments tell us that the rate equals K times the concentration of H2O2 times the concentration of iodide, the question is the decomposition of hydrogen peroxide an elementary process? So what has to be true for this to be an elementary process? The one thing that has to be true is that this has to be a single collision. So the question you have to ask yourself is, can a single collision result in H2O2 turning into H2O and O2? Now the answer to this is actually no. Because if this was an elementary step, then what would the rate law be? Right? The rate law would have to be second order with respect to H2O2. And our rate law that we're given, that's observed, is first order with respect to H2O2. So the reaction at the top of the screen here is not an elementary step. The other clue to tell us that it's not an elementary step is that the rate law includes some iodide, whereas there is no iodide in the reaction above. So this is definitely not an elementary step, not something that happens in one collision. So let's just try and propose a mechanism for this. So we have hydrogen peroxide plus iodide producing water and this IO molecule, and then IO reacts with hydrogen peroxide to produce water, oxygen, and iodide. So we're given the fact that the first reaction is slow, the second reaction is fast. So is this a reasonable mechanism? So first, let's see if the reaction mechanism, the reactions within there, the elementary steps, add up to the overall reaction. So we have 2 H2O2s, we have 2 waters, and 1 oxygen. So that's what we need for this to match our overall reaction. And we notice that we have an iodide on the reactant side of one reaction, an iodide on the product side for the other reaction, so that cancels out. And then we also have an IO on the product side of the first reaction and an IO on the reactant side of the second reaction. So both of those cancel out and we end up with the same reaction when we add up our elementary steps as we have at the top of the slide. So it seems like it's a reasonable mechanism, at least with respect to that. Now we have to check to see if the rate law matches what is on the previous slide. So what is the rate law of the slow step? If we just write that down, we're going to have rate equals K. And then again, we're looking at the first step. So we have H2O2 times I minus. So if we look at the previous slide, we'll also notice that this is the observed rate law. So our rate laws match. We can add up the elementary reactions to get the overall reaction. This is a reasonable mechanism. Okay, so I've already gone through most of this, but what I want to do is give a name to a couple of these components. We've already talked about this one. So the name for a component of a mechanism that is first produced and then used up, remember that's called an intermediate. But we haven't talked about this yet. So something that is first used up and then produced again in a later step. We'll talk about this a little bit later in the last section, but this is actually called a catalyst. Okay, so catalysts are interesting because they're essentially not used up in a reaction. Now, it's not completely true because there are other reactions that will eventually use them up. But if you think about it, in the first step, some of that iodide is being used to produce the products of the first reaction. But then the iodide is being reproduced in the second step. So the second step iodide can again be used in the first step to create the particular products it needs, and then it'll be reproduced again. Okay, so let's go through a couple examples. We have a reaction given above here. The experimentally determined rate law is determined to be rate equals K times the concentration of NO2 times the concentration of O3. And we're asked to identify the rate limiting step or the rate determining step in the proposed two-step mechanism. So this is a fairly simple question. I think by now you should be able to do this. Okay, so we're looking for NO2 and O3 in one of the elementary steps. They're both first order in the rate law, and they both have a stoichiometry of 1 in front of each of them. So the rate determining step in this case is step 1. So let's try another one. The rate law for the decomposition of hydrogen peroxide given here is observed to be first order in the concentration of peroxide. We're given another mechanism, so this is different than the one we just looked at with iodide. 1 slow step, 2 fast steps. So given that information, how do we write the rate law? So again, we're only looking at the slow step. So we got rate equals K times the concentration of H2O2. Right? Simple as that, because we only have to worry about the slow reaction. That's where the rate law comes from. Is the proposed mechanism consistent with the observed rate law? In the question, we're given the fact that the observed rate law is first order in H2O2. Our rate law that we determined from the reaction mechanism matches. It's also first order with respect to H2O2. And that answers C. Right? How do you know? Because they're both first order. Okay, so now here's something that will take a little bit of time to explain, and I have 3 examples that probably will take a little bit of time to go over. So far we've considered reactions that proceed in one direction, and as I said in the previous section, we will be getting used to reactions that go in reverse starting from chapter 14. So let's consider this proposed reaction mechanism. So we have 2 steps with an overall reaction and an observed rate law. Now, I want you to just look at that observed rate law and then the reaction mechanism. Notice that you can't derive the rate law from the reaction mechanism, right? Because we need to have an NO3 with a 2 in front of it in order for it to match this. And we also have to have an O2 in that same reaction. So we have an NO3 here, but we only have 1, and it doesn't have an oxygen beside it. In the first reaction, we have an oxygen, but we don't have an NO3. So how do we deal with this? So what if step 2 was slow and step 1 was fast and reversible? So we write these arrows here, one going forward, one going backward, to denote a reaction that can go both forwards and backwards. So how can we rationalize this? Can we make this particular reaction mechanism match the observed rate law? Okay, so how we're going to deal with this is to look at both of the reactions, both the fast and reversible reaction and the slow reaction. So we need to first write out the rate laws for the first reaction, both the forward and the reverse reaction, as well as the rate law for the second slow reaction. So for the first one, I'm going to call it rate 1, and that's going to equal K times the concentration of NO times the concentration of O2. That's the forward reaction. For the reverse reaction, I'm going to call that rate 2, and that's going to equal K times the concentration of NO3. And then for the second reaction, the slow reaction, I'm going to call that rate 3, and that's going to equal K times the concentration of NO3 times the concentration of NO. Now, these arrows again mean that the reaction is reversible, but it also means that the reaction is at equilibrium. So equilibrium means that the rate of the forward reaction is the same as the rate of the reverse reaction. So in other words, the reactants are making products just as quickly as the products are reforming the reactants. So if the rates of the forward and reverse reaction are equal, we can write rate 1 equals rate 2. And if we write that in terms of the right-hand part of each of these equations, we're going to have K1, K2, and K3 here, K1 times the concentration of NO times the concentration of O2 is going to equal K2 times the concentration of NO3. Now notice in the reaction mechanism we have an intermediate. NO3 is an intermediate, something that is formed and then removed in the next step. Now this intermediate is also part of the rate determining step, and that's an issue because the rate law shown here does not include that intermediate. But remember, the rate law must represent the slow step. So what we need to do is, in our rate 3 equation down here, notice our rate 3 also has that NO3 in it. We have to get rid of that. And the way we can do that is to solve the equation we just derived for NO3 and then substitute what we get from that into the rate 3 equation. So let's just solve this equation here for the concentration of NO3. That's going to equal K1 over K2 times the concentration of NO times the concentration of O2. Now we're going to take this part of the equation and substitute it directly into there. So we'll rewrite our rate law as rate overall. Rate overall equals K overall, and then we're going to write times K1 over K2 times NO times O2, and then we still have an NO left in our rate 3 equation, so we're going to write NO there. And since all of these rate constants, they're all constant, we can consolidate them into one rate constant. So for the final overall rate law, we can write it just like this. Rate overall equals K overall times NO. There's two NOs, so we're going to square that, times O2. Now, if we look at the rate law that we just derived from this reaction mechanism and compare it to the rate law that is in the question, right here, I just highlighted, we can see that both of these rate laws are the same. So this is how we would deal with this type of a problem. And I have a couple more examples. All right, so let's consider this reaction, nitric oxide and bromine. The observed rate law is given, and a reaction mechanism was predicted and proposed. So again, we have a reversible reaction as step 1 that's fast, and then a slow reaction as step 2. And notice again, we have an intermediate, NOBr2, that is in the second slow reaction, and it is not included in the rate law. So is the proposed mechanism reasonable? So now we have to take the reactions, and just like we did last time, see if we can derive the rate law from this particular mechanism. So here's the question again, and I'm going to go through this one a little bit more quickly, but it's the same steps as I went through on the previous slide. So first I'm going to write out rate 1, rate 2, and rate 3. Rate 1 equals K times the concentration of NO times the concentration of Br2. Rate 2 equals K2 times the concentration of NOBr2, and then rate 3 equals K3 times the concentration of NOBr NOBr2 times the concentration of NO. Okay, and we're going to consolidate these ones again since those are the reversible reactions. We're going to solve it for the intermediate being NOBr2. So let's just write it first of all as K1 times NO times Br2 equals K2 times the concentration of NOBr2. And then NOBr2 equals K1 over K2 times NO concentration times concentration of Br2. Okay, so now we're trying to figure out what the overall rate is, right? We're going to be replacing that NOBr with everything on the right-hand side of the equation that we just derived. So we're going to have our overall rate equals, I'm going to rate it as still K3 actually. I probably should have done this in the last slide. And later on we can write it as a K overall times K1 over K2 times NO and Br2. And then in our rate 3 we still have another NO up there. So our overall rate law is going to be overall K times the concentration of NO squared times Br2. Now we're asked to determine whether or not this is a reasonable proposed mechanism. So if we look back to see what the rate law is predicted to be, right? So here we are, K equals NO times the concentration of Br2. What we got was K times the concentration of NO squared times Br. So in this case, what we derived from this reaction mechanism does not equal what the observed rate law was. This has NO to the power of 1. Our rate law that we determined from this proposed mechanism has NO to the power of 2. So is the proposed mechanism reasonable? The answer to this one is no. So one last example. Given the following reaction mechanism, identify the rate determining step if rate equals K times the concentration of N2 times the concentration of O2 to the power of 1/2. So in this case, we're given 3 steps. So what we can do first is to ignore step 1 and see if any of the other 2 steps matches the observed rate law. So the observed rate law being a concentration of N2 times the concentration of O2 to the power of 1/2. So we would have to have in one of these steps both a nitrogen and an oxygen to the power of 1/2. And as you can see, none of the steps have that. So we're probably going to have to deal with step 1 as part of our reaction mechanism. And I'll start with using reaction 2 as the other one that will hopefully allow us to match the rate law with the observed rate law. So right now I'm assuming that this is the slow step. I'm not sure if it is, but I'm assuming it is. So here we go. Let's write everything down again as we did in the previous 2. Rate 1 equals K1 times the concentration of O2. Rate 2 equals K2 times the concentration of O squared. And then rate 3 equals K3 times the concentration of O times the concentration of N2. So these ones were the ones in equilibrium. So K1 times the concentration of O2 equals K2 times the concentration of O squared. And what do we have? We have an intermediate. Our oxygen is an intermediate, so let's solve for oxygen. So K1 over K2 times the concentration of O2, and the square root of that is going to equal O, right? The concentration of O. And again, we need the O because we have an O in our rate 3. So now our overall rate is going to be K3 times K1 over K2 times the concentration of O2, and this is all square root times N2. And remember, all those K's can be consolidated into 1, so we can end up with our overall rate equals K overall, and the square root of a number is the same as the power of a half, so we'll have O2 to the power of a half times N2. And if our rate law that we calculated or determined from step 1 and step 2 matches the rate that is observed, which it does, that means that we chose the step 2 correctly as being the one that is the slow step. Okay, so quickly, the last section that we're going to talk about in this chapter is catalysis. So we briefly did talk about it a bit. So a catalyst is a substance added to a reaction that increases the rate of the reaction but is not consumed. So I already explained the second half of this, something that is not consumed, but the main point of a catalyst is to make reactions go faster. So we can have what is called a homogeneous catalyst, which is a catalyst that is in the same phase as the reacting species. So if we have a bunch of liquid and we put in a catalyst that is also a liquid, that's a homogeneous catalyst. If we had a liquid and we put in something that is solid, then that would be a heterogeneous catalyst because it is in a different physical state than the reacting species. So let's just go through an example of how catalysts work. So this is the natural photodecomposition of ozone. So photodecomposition meaning that it's being decomposed by sunlight. So that's what ozone is supposed to do. It protects us from being exposed to high intensity ultraviolet light or UVC light by breaking down from the reaction of sunlight. So normally ozone reacts with sunlight to produce O2 and a singlet oxygen, and then actually this is supposed to be another O3 here. So another ozone can react with that oxygen atom from the previous step to produce a couple of oxygen molecules. So the net reaction is 2 ozones produces 3 oxygens, and the energy required for that to happen, or the activation energy, is 17.7 kilojoules per mole. Okay, so that again is the activation energy of the slow step. Okay, now CFCs, or chlorofluorocarbons, act as a catalyst in the decomposition of ozone. So these guys are quite stable in the atmosphere. If you remember from, I think, 2 or 3 videos ago, there was a slide that told you that the half-life of these guys is 50 years. So why they're so dangerous and why they do what they do is, first, they break down. So a CFC breaks down to produce a chlorine atom, and then that chlorine atom can insert itself into the decomposition of ozone. So now ozone is reacting with the chlorine to produce O2, and then that chlorine gas is then reproduced when the intermediate ClO reacts with another ozone, creating another chlorine. So that chlorine can then go back into the first reaction and react with another ozone and break it down. So notice that the net reaction is exactly the same. Okay, the ClOs cancel out because they're the intermediate. The chlorines cancel out because they're the catalyst. So we're left with 2 ozones, and there should be 3 oxygens here. So I'm missing an oxygen in one of these 2 reactions, but it's not critical. So notice that the energy for this, the activation energy, is 2.2 kilojoules per mole. So it's quite a bit less than the 17 that is required for the natural decomposition of ozone. So the blue curve on this graph shows the activation energies for the natural decomposition of ozone, and the red line shows the pathway for the catalyzed decomposition of ozone. So notice the activation energies are a lot smaller, and again, that means the reaction is faster. right? So this is the reaction that's going to happen in the atmosphere. It's going to happen more quickly than it would naturally, which is why back in the 90s we had a big hole in the ozone layer. Now, most of you were probably either not born or very young, so you probably don't remember it, but that was a big thing back in the late 90s. Now, this red line will actually go down to the same level as the blue line because the catalyst doesn't change the products or the energy of the products. It only changes how quickly the reaction goes from reactants to products. Okay, so a couple of examples. In most vehicles, there's a catalytic converter, which is a heterogeneous catalyst. So what happens there is that the nitrous oxides that are produced by burning fossil fuels, they are not good for the atmosphere, right? If we go back to the first slide of this first section in chapter 13, that was showing you how NO and NO2 produce photochemical smog. So the catalytic converter tries to convert these into both nitrogen gas and oxygen gas, which are obviously things that are present naturally in the atmosphere. So what the catalytic converter does is it helps with the orientation of the molecules. Okay, remember, orientation of a molecule is something that is required for a reaction to occur. So the catalyst helps to stabilize those molecules on its surface, allows them to be in the right orientation, and helps them to react to produce N2 and O2 molecules from the more harmful NO gases that are produced. Okay, another example is a biological catalyst. If you take biochemistry, you'll learn about this a lot more. So we have an enzyme and a substrate. So the substrate is the thing that the enzyme is reacting with to produce, in step one, this enzyme substrate complex. So here's the enzyme. Here's an active site of that enzyme, so that's where the reaction is going to occur. So this substrate, this thing, that part of the molecule can fit just nicely in the active site. So here's the enzyme substrate complex, and then the enzyme does its thing. It orients the molecules in such a way that they can do whatever reaction they have to do, and then we get out of it the product. So again, we have a graph showing the uncatalyzed reaction having a much higher activation energy than a two-step catalyzed reaction shown in red, which has a lower activation energy, which means that the reaction should be faster. So that's what enzymes do. They make reactions go faster. They make them go at the speed that they have to go at in order for life to persist. Okay, so that's all I have for this chapter. In the next chapter, actually the next few chapters, we'll be talking a lot about equilibrium, what it means, and about reactions that go both forward and backwards. So as usual, if you have questions, you know where to find me.